Hello, my name is Rene Demets. I'm a biologist working at ESTEC in Noordwijk in the Netherlands. And during this lecture I will tell you more about EXPOSE. That is an exposure facility for astrobiological experiments. I will start with a PowerPoint presentation about the history of the panspermia theory. That is one of the theories that is being tested with EXPOSE. Next, I will show you some instruments that have been used before for exposure experiments in space. The Russian KNA and the ESA Biopan. And then I will show you a model of EXPOSE, a real one that was in space in 2009, and I will tell you how it works and what it looks like. Next, we compiled some footage made by NASA about the installation of EXPOSE at the outside of the ISS. And that is mixed with some pictures, some photographs that were made by the astronauts during that same EVA. Next, again a series of PowerPoint slides, now addressing the environment of the EXPOSE experiments. What do they see in space in terms of temperature, pressure, ionizing radiation, UV and microgravity? And finally, I will address the plans that we have developed about future experiments, exposure experiments in space. There are three types of experiments conducted in EXPOSE. First, it is exposure of chemical samples to the space environment. Second, it is exposure of biological samples to the space environment. And third, it is exposure of biological samples to simulated Martian conditions. But what is the scientific rationale? In the following slides I will give you the background of the Group 2 experiments. That is why astrobiologists want to know to what extent terrestrial organisms can cope with the space environment. A clue was already provided by Professor Onofri in one of the earlier lectures. It is to check the panspermia theory. According to that theory, life can move through space from one celestial body to another by natural means. It's a fascinating concept and perhaps it is true. We go back in history. In the middle of the 19th century, a tremendous amount of scientific breakthroughs occurred. And here is a short list of ideas and findings that are important to understand the basis of the panspermia theory. First on the list is Christian Ehrenberg. He claimed that microbial life is present in the upper layers of our atmosphere. He had collected evidence that spores soaring high up in the air and coming from Africa can cross the Alps and land in Central Europe. The second on our list is Charles Darwin. He wrote that all terrestrial life probably stems from one common simple ancestor. Number 3 is Louis Pasteur. Pasteur is known for his sterilization experiments. Before Pasteur, it was thought that simple life could spontaneously emerge from filth and from old food. Today, of course, we say it was infected by life. And number 4 on the list is Camille Flammarion. He claimed that carbon compounds that had been discovered by chemists in some meteorites most probably represent the remnants of extraterrestrial life. And now a new face, that is Herman Hyster. He had read all these reports and he was able to synthesize all these ideas from Ehrenberg, from Darwin, Pasteur and Flammarion. And he wrote in a quite famous article from 1865, "Our common ancestors, consisting of simple microscopic life, may have arrived on Earth on a meteorite that came from space. And conversely, terrestrial microbes might be removed from our atmosphere by meteoroids, I must say, or comets passing by to be deposited on another uninhabited celestial body, to initiate there a new biosphere." But who was Herman Hyster? Not so much has been published about him. he was familiar with botany. He studied medicine and he became a physician and was appointed as a professor. He was famous for his excellent lectures and he wrote a tremendous amount of publications and books, and at one point he became a part-time politician in Dresden, where he lived. Later on he moved his interest to microbiology, and most of all he was the editor-in-chief of Schmidty Yearbooks. And what is that? You will see on the next slide. Schmidty Yearbooks, in translation Schmidty Yearbooks, was an annual series of scientific review books with critical reviews of everything that had been published over that year in the scientific field of medicine, plus some biology and also some chemistry. Richter published his story, his panspermia theory, in that journal. So he published his own story in his own journal. And the title of that publication was Zur Darwinschen Lehre, that is about Darwin's theory. Richter had read in a German translation The Origin of Species, and he was somewhat disappointed that Darwin wrote nothing about the beginning of life on Earth. And in this paper, Richter offered a theory to fill that gap. The earliest life could have arrived on Earth on a meteorite. Where lived Herman Hyster? He was working in the city of Dresden, in the kingdom of Saxony, Sachsen. Only 6 years later, in 1871, Saxony became part of the German Empire, das Deutsche Reich. In short, he was an extremely talented and well-read Saxonian physician, and he was the author of the first scientific paper about panspermia, published in 1865, and he provided the first rational concept that life may be transferred through space by natural mechanisms, and he was the very first to do so. So he is the real pioneer. But oftentimes you can read that that theory was initially proposed by William Thomson, later known as Lord Kelvin, or even Hermann von Helmholtz or Svante Arrhenius. Here in this overview of the chronology of the publications you can see that Richter was first. Next was Thomson and Helmholtz and then Arrhenius. So why was so much emphasis paid to Thomson, Helmholtz and Arrhenius, not so much to Richter? Richter was a local hero. Thomson, Helmholtz and Arrhenius were international celebrities, even at that point in time when they first came with that theory. Everybody knew them, and whatever they said or wrote was taken extremely seriously and was widely distributed over the whole world. Now, a question is, how relevant is the panspermia theory today? Astrobiology is the study of the origin, evolution and distribution of life, and it is often claimed that the panspermia theory is not that useful because it tells absolutely nothing about the origin of life. It just tells that life perhaps came from elsewhere, but how it originated on that other place was not mentioned, was not part of the panspermia theory. Yeah, the panspermia theory tells a lot about the evolution of life. That is the second theme in the list of major themes within the astrobiology. It's origin, evolution, distribution, now evolution. It seems that the earliest fossils that we know of on Earth are 3.5 billion years old, perhaps even 3.8 billion years old. In fact, that is still intensely debated. However, if that is true, if that is the true age, there would have been almost no time for chemical evolution to happen. That is the preparatory step in nature to make biological evolution happen. Chemical evolution would be squeezed between the late bombardment, that is the red bar in this picture, and the onset of life on Earth. That puzzle was never properly resolved. If the earliest life on Earth was, however, imported from space, then that puzzle can be resolved. And the third theme of astrobiology, that is the distribution of life. And now a sentence that perhaps looks pretty weird. The panspermia theory connects terrestrial life with extraterrestrial life. Now I'm not talking about science fiction, and it is also not a philosophical statement. What I would like to say is this. Let's assume that one day in the coming years extraterrestrial life is discovered. Not that green man here, but let's say primitive life on Earth, microbes. It could be that chemical analysis reveals that this Martian life is based on DNA and on RNA and perhaps on the amino acids as we know them from Earth. A possible conclusion may be this discovery proves that life can only emerge according to a standard biochemical pattern. In nature there's just one biochemical and biophysical way available to establish life. But there is also an alternative conclusion possible. The commonality in DNA, RNA and amino acids could be due to the fact that Martian life originated on Earth, or vice versa, that terrestrial life originated on Mars, or that terrestrial and Martian life are descendants of the same ancestors which came from elsewhere, from a third place. This alternative conclusion, assuming a kinship between life on Earth and life on Mars, we are family members, hinges on the credibility of the panspermia theory. So in conclusion, yeah, it makes perfect sense to verify if the panspermia theory is correct or not. It is still a relevant theory today. So thank you Mr. Richter, Helmholtz, Thomson and Arrhenius for developing this theory. In front of me is an exposure pen called the KNA, the Container Naoutnoi Apparaturi. That's Russian for container with scientific equipment. A container for scientific equipment. This pen-shaped structure was bolted at the outer surface of Bion and Photon capsules. Here you can see the screw holes. And it was equipped with a lid that was fitted to the bottom structure with a huge spring. The KNA is launched in the open position with the lid held open by a strap, by a cord. The experiments inside, sitting here and also here, are only protected during launch by the nose cone fairing of the rocket, nothing more. By the end of the flight, that cord was released and the lid slammed down, turning this into a closed and sealed experiment compartment protected by a heat shield. This surface was exposed to the re-entry conditions, lots of hot air. ESA was involved in experiments in the KNA during 1987, 89 and also in 1992. This looks very simple and in fact it is still being used. By the end of April this year, 2013, there is a new Bion flight in the planning equipped with 4 of such pans, 4 KNAs. It looks quite simple, but it does its job. We are now in the Space Expo, a space museum next to ESTEC. And in this museum there is a real model of the Biopan on display, this one. The Biopan completed 6 missions between 1992 and 2007. And this is probably the one that flew in 1999. The Biopan consists of 2 main parts. Here's the bottom part that is screwed to the outer surface of the Photon Capsule. The other part is the lid, and the lid can be opened by telecommand from ground. By the end of the flight, the lid is closed again by telecommand, and the whole structure, the bottom part and the lid, are protected by a heat shield, an ablative heat shield. And you can tell from the condition this heat shield is in that it really underwent a re-entry. The heat shield is thin on this side and it is much fatter on that side. That is because the Biopan was entering with this side, with the fat shield in front and the thin side at the rear. The Biopan was a real multi-user facility, as we call it. It could carry 4 up to 10 different experiment packages provided by different investigator teams. It was equipped with plenty of sensors to reconstruct the full environmental history that the samples underwent. When those 6 missions had been completed, the program came to an end. A drawback was that the samples could never be exposed for a longer duration than 2 weeks. That was due to the fact that there was not more power provided by the spacecraft. The spacecraft was not equipped with solar panels, but with a huge battery pack. And the battery pack supplied energy to lots of different payloads. And usually the flight was restricted to only 2 weeks. The investigators were asking for a longer duration exposure, and that came to with the introduction of Expose. Now we are back at ESTEC in the Erasmus High Bay. That is to show what the place was on the satellite of the Biopan. Here is a picture of the Photon Capsule. Photon Capsule was approximately 6 meters long, and the Biopan was positioned here. In this picture it is rendered in the open position with the lid open. It was here. The Photon Capsule is a recoverable capsule, but the only part that is really recovered, that comes back on Earth, is that ball-shaped structure with a diameter of 2.2 meters, and that structure is standing here next to me. That is the real re-entry capsule of Photon 12, flown in 1999. The Biopan was sitting here. You still see that circular surface with screw holes. That was the place where Biopan was sitting during the flight. The re-entry capsule is spherical, it is ball-shaped, but still it has a nose and a tail, and you can tell by the color of the heat shield. Here the brown area was not that much affected by the heat, but here the color turns from grey to even light grey, sort of ash. That was the hottest point, that is the stagnation point. Underneath, in the middle, is the stagnation point. That means the capsule was entering the atmosphere with that part in front and that part at the rear. And the attitude is stabilized due to the center of mass that is not in the middle. That's why it keeps its attitude during re-entry, with a front end and a rear end. This window is of course only for exhibition purposes. In the real thing it was protected by a solid cover with heat shield material. In front of me is Expose E, the real flight hardware. This instrument was really in space in 2008 and 2009. The size is approximately a suitcase, and that structure here is a big bracket to attach exposed to the outer surface of the space station. On the upper side are 3 strips, 3 trays to accommodate the samples. And each tray is divided in 4 sections. Each part is called a carrier, a sample carrier. The sample carriers are covered by a window, and the window is made of quartz or magnesium fluoride. That is to allow solar UV to reach the samples. There is a second layer of samples inside. I cannot show them to you, but in reality there was a double set. The second set is in the shadow all the time during the whole flight. So after flight you can identify what the specific effects have been of solar light. Solar sun illuminated samples in comparison to shaded dark samples. Here in an upright position is a flap, a cover, and that flap could be closed and opened. That is to regulate, to control the amount of solar light reaching these samples. This strip of samples was without a flap, without a lid. The movement of the flap could be controlled by telecommand from ground, but now I will do it from that laptop. Close the shutter. Look, it's operated by an electrical motor inside. And I will open it again. To measure the amount of sunlight, Expose is equipped with 5 sensors. 4 are sitting in the corners, 1, 2, 3 and 4. These are UVB sensors, and there is one major sensor here, a radiometer, receiving a wide range of wavelengths. The individual carriers could be adjusted according to the needs of the investigators. The interior could be evacuated just by opening a simple valve to make a connection between the interior of that carrier and the outside environment, space vacuum. Alternatively, these carriers could be closed and sealed to be occupied by a neutral gas like argon, or even by a simulated Martian atmosphere. That is to test how well our terrestrial organisms would behave under Martian conditions. What we do not do is to monitor the behavior of the samples during the flight. Now, the samples on Expose E were for 1.5 years in space, and the investigators could investigate the difference between the status of the samples before flight and after the flight. But if any changes were introduced during the flight, we cannot pinpoint how that happened, at which moment. That is still something for the future, for a more futuristic piece of equipment, that we can follow the changes over time during the flight. Here is a 1:5 scale model of the Columbus module. Expose E was sitting in this position with the windows pointing upward. So again, that was starboard. The flight direction of the ISS was here, and the windows were pointing up. Experimentation in space is difficult. One of the difficulties is that we are not there. When you run your own experiment in the lab, you know exactly what's going on, and you can check your experiment every minute if you like. An experiment on the space station is completely different. You make your preparations on ground, and then it is handed over to ESA in this case, and your experiment package disappears. And you can only stay informed about the conditions of your experiment indirectly. That's even true for us. We're working here at ESTEC, but I have not a direct visibility of the experiments that are going on in the Columbus module or outside the ISS like EXPOSE. We've only indirect information. There are many layers of information. We cannot even speak to the astronauts or cosmonauts. That is done indirectly. We can forward a request. We want to pose a question, and it takes a long time before we have the answer. EXPOSE is sitting at the outside of the ISS, and sometimes we have some direct information about what is happening. And NASA was very helpful during the installation of EXPOSE at the outer side of the ISS. They provided some live video material which everybody could watch on the internet, and so I did. But unfortunately, that footage is very difficult to understand. And now I will make an attempt to show you some pieces of that footage of the installation of EXPOSE, plus some pictures that were made in that same period, in these same minutes, by the crew. And we have combined it here at ESTEC. We have made a short summary, and we will give some supporting information to make it easier for you to understand what really happened. EXPOSE was taken out of the ISS by 2 astronauts. In fact, one real astronaut, Mike Finke, and the other one is called a cosmonaut, a Russian astronaut. His name was Yuri Lonchakov. Mike Finke and Yuri Lonchakov, they left the ISS through a hatch in the Pirs module. Pirs is placed on the Russian segment, and Pirs is Russian for pier. That's the place where a boat docks, undocks in the harbor. These 2 persons, Lonchakov and Finke, went outside and they took EXPOSE with them. Everything is happening in near weightlessness. It means they could not put the EXPOSE solidly in a place before they started working on EXPOSE. They had a long working schedule in front of them, and EXPOSE was not the first task they had to fulfill. They had to do much more. So they took EXPOSE out and just kept it floating, attached by a tether, so that it could not drift away into space. That would be a big loss for us. It's a costly instrument, some millions of euros, so they should be very careful. Anyway, when you look at the footage that will be displayed soon, there's also one thing you should know. The footage is made upside down. So what is up on your screen, that is the Earth, and what is down, that is deep space. And I do not know for what reason the cameras were making the recording in that way. You will also see that the text Pirs and later Cosmos, written on these modules, is reversed, is upside down. Anyway, let's start.
This is Mission Control Houston, 45 minutes into today's spacewalk that got underway at 11:22 a.m. Central Time. You're looking at Mike Fink on the right side of your screen. Yuri Lonchakov at the top of your screen wearing the Orlan or Russian spacesuit with the blue stripes, Fink with the red stripes. Well into the second spacewalk of their increment, the 6th for Mike Fink's career, the 2nd for Lonchakov, as they wrap up work with the removal or the shortening of a half-dozen straps right around the docking interface between the Progress resupply vehicle at the top of your screen, the Progress 32, and the Pirs docking compartment. The Pirs serves a dual purpose, both as a docking port for arriving Russian vehicles and an airlock for Russian segment spacewalks. Fink and Lonchakov, once they clean up the work site, will move on to the side of the Zvezda service module to begin what is expected to be about an hour-and-a-half long task to install and activate a European materials exposure experiment called EXPOSE-R that they attempted to install and activate back in their previous spacewalk on December 22nd and 23rd, but a cabling problem inside the Russian segment of the space station prevented the experiment from being activated. The cables were reconfigured once Expose was brought back inside the station for troubleshooting by Lonchikov. It is expected to work like a charm this time, this being the major objective of today's spacewalk for Lonchikov and Fink, a spacewalk expected to last somewhere in the neighborhood of about 5 hours and 45 minutes. About to begin to make their way with the Expose-R, the European Materials Exposure Experiment, down to the side of the hull of the Zvezda service module to begin its installation and its electrical cable connection.
Look here, progress and Piers is written upside down.
Activate that experiment.
For the reason that I explained earlier. That is Expose, and it's floating in weightlessness. There was no parking place to have it fixed before it was properly installed. So they just keep it floating. Of course it is attached by a tether.
Michael, where are you going? Where are you rushing? I'm here. I'm near the view ladder. I can take photographs from here and the windows number 8, number 6.
Again, the Expose is highlighted in this picture. The astronaut and the cosmonaut are doing something completely different.
Russian flight controllers now in the process of disabling thrusters on the Zvezda service module as Fink and Lonchikov begin to make their way to the various work sites that they will be conducting most of the rest of the day's work. The installation of that Expose-R experiment, the European Materials Exposure Experiment.
Yeah, he said Materials Exposure Experiment. It was, of course, biology and biochemistry.
I am going to take photographs of you now. I vote for it.
We got the pictures only later, but from that footage we know exactly when these pictures were made.
Just a second. Did you take a picture? Yes, I did. I would like to take another one.
Red stripes, that is Finke, Michael Finke.
Work, getting to the work site to set up all of their tools and equipment for the installation and ultimate activation of the European Exposure.
Yeah, unfortunately, behind a solar panel.
Inside that suitcase-like device called Expose-R, they will be releasing cables from a series of spring clips, opening up thermal protective covers, and then we'll hook up
all these pictures were taken during that EVA
service module that run internal to the Russian segment of the International Space Station to provide electrical power for that European experiment that is expected to remain bolted to the hull of the Zvezda service module for about 14 months, collecting scientific data.
We have them on already.
The ground track.
And wasting little time, Yuri Lonchikov confirming that the Expose-R experiment has now been installed on a bracket on the side of the Zvezda service module. That is the first of a series of steps.
Okay, taking a picture of the Expose-R and surroundings. Copy.
Expose-R with a lid still on top.
Houston, 1 hour 43 minutes into today's spacewalk by Mike Fink and Yuri Lonchikov in Russian Orlan suits outside of the Piers docking compartment. Fink and Lonchikov are taking photographs and taking up a cable slack using wire ties for the European Expose-R materials exposure.
And here's Michael Finke removing the lid.
Was just installed and successfully activated.
And we have to take picture of the impulse.
Yeah, the first pictures with the lid removed. These are close-ups, and later on you will see a composition of all these close-ups.
When you take pictures, These pictures
That's blue stripes, that's Yuri Lonchakov.
This is Mission Control Houston, approaching the 2-hour mark into today's.
That's the composite picture.
And Mike Fink.
Okay, exposed R looks beautiful. We can see everything. And
the composite picture again.
Copy, Michael. Please do.
Expose is located at the outer surface of the space station, and in the following I will explain to which extraordinary environmental conditions the test samples were subjected to in space. The test samples on Expose are subjected to a combination of 5 special space factors. Firstly, ultraviolet light from the sun. All samples are placed behind UV transparent windows at the top surface of Expose. Second, vacuum. A vacuum is achieved by opening a gas valve to the sample compartments. Third, there is cosmic radiation. And fourth, there is an unstable temperature. The temperature of the test samples on Expose is not controlled. We do not have heaters or coolers. Temperature moves up and down. And fifth, there is microgravity or weightlessness. This package of 5 factors cannot be replicated on ground, and that's why we run those experiments in space. To understand what these samples are experiencing, I have to tell you more about the rhythms. In orbit, the test samples are not continually in the sun, and that is due to 2 different rhythms. A fast rhythm, that is the orbital rhythm, and a slow rhythm, that is the beta angle rhythm. And the temperature follows those rhythms. First, something about the orbital rhythm. Every day the ISS flies around the Earth 16 times. 16 orbits are completed every day. And the duration of one orbit is 92 minutes. And during each of those orbits the ISS crosses the day side and the night side of the Earth. And during the day there is sun shining on Expose, the temperature moves up, and during night the temperature drops down. And the result is an oscillating temperature and also an oscillating ambient pressure. We know that from our conditions here on Earth. We have days and nights. During the day temperature is higher, but here the oscillation is much faster. Here's an example. During 7 consecutive orbits, the irradiation on Expose by solar light was measured by 4 sensors. Each colored line represents a single sensor. 2 sensors produced a strong signal, 2 other sensors a weak signal. The explanation is that the sun was shining over that period, not vertically on top of Expose, but it came from the side. But more important for our understanding is the rhythmicity. Every 92 minutes there was a peak, and every 92 minutes there was also a period of no sun, of darkness. Sunlight, darkness is alternating. The picture illustrates that the test samples on Expose experience one day and one night every 92 minutes. In this picture, the temperature recordings are superimposed on the previous slide. The presence and the absence of solar light create a temperature rhythm. The temperature here was recorded by 9 sensors, all with a different color. Each time solar light was received, the temperature went up, and every time exposed flies into the night, the temperature sinks down. As a consequence, the test samples were subjected to a temperature rhythm with a period of 92 minutes with an amplitude of about 10 degrees Celsius. This picture also shows something else. During those 7 orbits, the overall temperature went slowly up. We will come back to that later. The ISS orbits at an altitude of approximately 350 kilometers. At that altitude there is no perfect vacuum. There is still some very thin air. The pressure of that rarefied air periodically moves up and down around 10 to the minus 10 bar. That is less than 1/1000th of our terrestrial pressure. And the period of that rhythm is again 92 minutes. It means that exposed crosses during each orbit a zone of higher pressure, that's at the day side of the Earth, and a zone with lower pressure at the night side of the Earth. Inside the sample compartments, that same rhythm is displayed. So it is felt, it is experienced by the test samples. The test samples on expose are not only exposed to vacuum, there is usually also a subset in closed sealed compartments. These are kept at 1 bar. That's for comparison, to check what exactly the difference is between exposure to vacuum and exposure to normal pressure. There's also a third option available, that is to put the samples in a Martian atmosphere. That Martian atmosphere is a simulated Martian atmosphere, of course. It is mixed here on Earth. And some compartments, again sealed compartments, are filled with that Martian mixture at a pressure of 0.01 bar. That's 1% of the pressure here on Earth. In all 3 cases the pressure moves up and down following the solar irradiance. Now a second rhythm, that is a slower rhythm, it's called the beta angle rhythm. This one is more difficult to understand, so please have a close look at these 2 pictures. The clue is the orbital plane of the ISS slowly rotates with respect to the Sun. Sometimes the ISS is in the Sun continually during a full orbit, look at the picture at left, but on other occasions the ISS is completely in darkness during part of the orbit, that's the picture at right. And in the second case, picture at right, there are moments that the Sun is shining vertically onto the top surface of expose. Here we will expect a peak in the temperature recordings. We could see that the amplitude of the orbital rhythm was close to 10 degrees Celsius. Temperature moves up and down over a span of 10 degrees Celsius during each orbit. In this picture, the beta angle rhythm, the amplitude is much higher than that. It's close to 60 degrees Celsius. And the samples on expose apparently experience periods of hot temperatures alternating with periods of low temperatures, like our summers and winters. The red stripe in this picture is about 10 degrees Celsius thick. That is due to the fact that the orbital rhythm creates differences of 10 degrees Celsius, but you cannot see that fast rhythm in this picture because the horizontal axis has been compressed. In this slide, the temperature history over the complete mission of Expose R is plotted in such a way that you can see how much time is spent by the samples at different temperatures. Most of the time the samples were sitting at a temperature above 0 degrees Celsius. The average temperature was 19 degrees Celsius. And a minor part of the time was spent below 0. But due to those rhythms, there were lots of zero crossings, the temperature moving up and down through 0 degrees Celsius. On Expose R, a flight of 22 months, there were 569 zero crossings. That would correspond to 285 freeze-thaw cycles, but of course only in case there was water included in the samples. This picture shows the amount of solar light that was seen by the samples. It is expressed as the daily dose, the average daily dose. On Expose E, the daily dose was 1 to 2 kilojoule per square centimeter, and in fact that number is not very much different from what we experience here on Earth in the tropical zone. On Expose R, much higher values were recorded. The average was 2.5 kilojoule per square centimeter, and that is much higher than what we know from the tropical zone on Earth. The difference is due to the fact that the shading conditions on Expose E and Expose R were different. The samples on Expose R were better exposed to the sun, you could say. There was also a difference in flight duration. Expose E was in orbit for 18 months and Expose R for 22 months. And the total effect was that the sun-exposed samples on Expose R received twice as much solar light as the samples on Expose E. That was due to the higher daily dose and to the longer flight duration. We have addressed the quantity of solar light. Now about the quality. The wavelength spectrum of solar light in space is different from the wavelength spectrum here on Earth. That is because the lower wavelength ranges are blocked out by our atmosphere. The yellow part in this picture is the pure solar light emitted by the sun. And these wavelengths are all received by Expose. Here on Earth we receive the red zone, and the red zone is lacking the smaller wavelength ranges of the ultraviolet light. That allows us to investigate specifically biochemical and biological effects that are created by solar UV light. That type of light cannot faithfully be replicated on Earth. So it's very good that we have the opportunity to run those tests on Expose. In a typical experiment on Expose, the samples are accommodated in two layers. There is a top layer with the sample sitting behind UV transparent windows, accompanied by a lower layer, a bottom layer with exactly the same samples, a duplicate layer, in darkness. And after the flight we can easily check what the effect was of solar light by comparing these two sets of samples. Some samples in the top layer are usually protected against an overdose of UV by a sort of sunglasses filters to attenuate the dose of UV. The next space factor is ionizing radiation. Radiation in space consists of soft particles, low energy particles, electrons, protons, and the hard particles, the high Z particles. Space radiation hardly reaches the surface of our Earth due to collisions with molecules in the atmosphere. To get a better idea of what's going on Expose, let's have a look at the depth curve. This curve was made at the outer surface of the ISS. The vertical axis is a log scale, that's important to know. And the vertical axis is expressed in gray. 1 gray is the absorption of 1 joule of energy in the form of ionizing radiation per kilogram of matter. And the horizontal axis is a linear scale expressed in grams per square centimeter, and that is the shielding density. That is how much material is placed in front of a detector to stop, to reduce the incoming radiation. As indicated in this picture, beyond 2.5 grams per square centimeter, additional shielding becomes ineffective. And due to the fact that the vertical axis is a log scale, even that thin layer of material stops most of the incoming radiation expressed in grays. However, there is a type of radiation, the hard particles, that cannot be stopped at all. And these are the most dangerous particles when it comes to biology. All the test samples on Expose are contained behind glass, and that glass stops most of the incoming electrons and part of the protons. The dose rate of ionizing radiation on Expose is in the order of a few hundred microgray per day. Comparable doses have been recorded inside the ISS. So it is not so that by moving our samples outside, exposing them externally at the outer surface of the ISS, we receive much more cosmic radiation than inside. That is due to the fact of the depth dose curve in the one of the previous slides that shows that even a quite shallow layer of aluminum blocks out all these soft particles. The last factor, the space factor that I would like to address is microgravity. The word itself is quite confusing. Microgravity has nothing to do with micro, that is 10 to the minus 6. It is not even related to a reduction of gravity. Microgravity, as we experience it on the ISS, is better called near weightlessness. So our samples are almost without any weight on Expose. Near weightlessness is obtained in all objects that are freely falling and exposed, and the test samples are freely falling around the Earth within an environment at almost 1 G. That is the pull of the Earth. Microgravity is, for the Expose experiments, not very relevant, because weightlessness mostly affects organisms that are in action, that are growing, developing or reproducing. We are working with dormant organisms like spores and seeds and desiccated lichens, films of organic molecules, and those are not significantly affected by the absence of weight. A summary of the experiment environment. Expose offers long duration exposure to full spectrum solar UV. That is impossible to replicate on Earth. And typically the test samples are accommodated in 2 layers, a top layer in the sun and a bottom layer in darkness. That's for comparison. The temperature moves up and down. The mission average is 19 degrees Celsius. The temperature moves according to 2 rhythms, a slow rhythm, comparable to what we have on Earth in summers and winters, but then about 6 times accelerated. Superimposed on that is a fast rhythm, the day-night rhythm, approximately 16 times accelerated. Pressure. If the samples are exposed to the ambient pressure of the ISS, the pressure is less than 1/millionth of the pressure on Earth. And optionally the samples can be put in sealed closed compartments at a normal pressure, that is for a straight comparison to the vacuum conditions, or to a Martian atmosphere, or to any other atmosphere relating to a non-terrestrial celestial body. Cosmic radiation, the dose levels that have been recorded on EXPOSE are comparable to the dose levels that were recorded inside the ISS. Microgravity is less relevant to the EXPOSE experiments, and in fact it is better called near weightlessness to avoid any confusion. The results from EXPOSE E have been fully published last year in May in a special issue of Astrobiology. The results from EXPOSE R are still to be published, that is in preparation. I will not address the results. I'm working here at ESTEC. We are in charge of managing the flight campaigns and making sure that all instruments are working well. I leave the results to the scientists who are not working here at ESTEC but distributed all over Europe at different research institutes. But if you want to learn more about the setup of the experiments, what was on board of EXPOSE E and EXPOSE R, you are kindly invited to address the Erasmus Experiment Archive, and here in this slide you can find the website addresses. To summarize what we have seen so far, first we had a look at the early history of the development of the panspermia theory, 150 years back, and we had a look at exposure facilities starting with the Russian KNA, from which the ESA Biopan was developed. Then we had a look at EXPOSE, and I could show you the real model that was in space in 2008-2009. Then we had a look at the footage made by NASA about the installation of EXPOSE R on the Russian module Zvezda of the ISS. And that was mixed here by pictures taken by the astronauts during that same EVA. Then we had a presentation, PowerPoint presentation about the experiment environment on EXPOSE. And perhaps now it's time to look in the future. What will we do next? After 2 missions, EXPOSE will be in space once more in 2014, according to the latest planning. It's called EXPOSE R2, with a new set of experiment samples. And there is even a new instrument under development called OreoCube, devoted to astrochemistry. And there is some novelty here, a new feature. We will be able to monitor the behavior of the samples in real time during the spaceflight, something that we could not do before. I hope you enjoyed this lecture, and perhaps see you later on a new session of ABC lectures. At exposure facilities starting with the Russian KNA, from which the ESA Biopan was developed. Then we had a look at EXPOSE, and I could show you the real model that was in space in 2008-2009. What I could not show you was a big instrument called the Eureka, which is not on display here at ESTEC, so I could not show you that beautiful instrument. Then we had a look at the footage made by NASA about the installation of EXPOSE R on the Russian module Zvezda of the ISS. And that was mixed here by pictures taken by the astronauts during that same EVA. Then we had a presentation, PowerPoint presentation about the experiment environment on EXPOSE. And perhaps now it's time to look in the future. What will we do next? After 2 missions, EXPOSE will be in space once more in 2014, according to the latest planning. It's called EXPOSE R2, with a new set of experiment samples. And there is even a new instrument under development called OreoCube, devoted to astrochemistry. And there is some novelty here, a new feature. we will be able to monitor the behavior of the samples in real time during the spaceflight, something that we could not do before. I hope you enjoyed this lecture, and perhaps see you later on a new session of ABC Lectures.